So this is the first algorithm. This is called iterative policy evaluation. And if you see here in the inner loop, we need to apply the Bellman equation for every possible action A in your MDP, for every possible next state S prime, okay, and for every possible state S. This is the policy function, this is the transition function, this is the reward function, and this is the value function. Gamma is our discount factor, and it could take a value between 0 and 1. So what you do is, if we look at this loop here for each S in our state set, so you need to apply this for every state in your MDP. In the previous example where we had 3 states, then we will need to apply this for state 1, state 2, and state 3. So that's basically what the algorithm does to update the values. You initialize the values, as you can initialize them with 0, and then you just keep applying this rule. Okay. Now the algorithm also has these lines here, this delta, this v here, and this theta, and these are used just to define stop criteria. So let's see how they do it. So they say here, repeat this until this criteria is correct, is true. Okay, so theta is going to be a small positive number. So this is like saying if our delta is less than this size of error, I will consider that that's enough and I will stop my algorithm. Now, how you define this theta in your algorithm is a bit tricky, because it depends very much on the values of the states, and the values depend on the reward function that you are going to use. So for some problems where possible the rewards are in the range of I don't know, between 0 and 10, maybe some theta of 0.01 is good, but maybe if the rewards are between 10 and 1000, this theta is not going to work for that problem. So it's a bit tricky to define this, and you need to experiment a bit to get the right theta. Okay, so this is just an error measure for stopping the algorithm. You initialize the delta to be 0, and then what you do is you store the value of the first state that you are going to update. So suppose that you are going to work first with state 1. So you look at the value for state 1, which initially is 0, and you will store it in this V. Okay. Then you update the value for that state 1, and what you do is you compare what is maximum, what is larger, delta or the difference between the previous value of state 1 and the new value of state 1. So you compute this difference, you consider only the absolute value, these bars are for absolute value, and then you just compare with delta. If this difference is larger than delta, so if that is the maximum, then you will assign that value to the delta. So that's going to be the new value for delta. Then you go again and you do the same for state 2. So you first store the current value for state 2 in V. You update the value for state 2, and then you compare the difference between the previous and the new value for state 2, and you check if that difference is larger or not than the previous delta. The previous delta stores at this moment the difference between the previous and the current value for state 1, if you remember. So you are going to say, okay, this difference is larger for state 2 or for state 1. If it is larger now, then that will be the new value of delta. If not, you will keep here the difference for state 1. You go one more turn for state 3, store the current value of state 3, update the value of state 3, and then you go and check again. If the change that the state 3 suffered is larger than the delta, you replace delta, otherwise you stay with the same delta. So after you have done this for every state, in this case 3 states, you have performed a complete sweep. In order to obtain the final value state, you need to complete several sweeps. Okay, and in the case of the application of this rule, you must consider that here it's saying the sum for every action. So in the previous example we had only 2 actions, so this will be applied for action 1 and for action 2. So this sum represents really 2 terms in our sum, but inside this, the first term, you will have this product here that is telling you another sum, and this sum will be for each of the possible next states. In our previous example we had 3 states, so this sum will contain 3 terms. Okay, so you need to develop these sums, and you will have the complete expression that you will need to update the values. So here we're saying that the main sum will contain 2 terms, and each of the terms of this main sum will contain 3 terms defined by this sum. Okay. So this is important to know. Again, if you had, instead of 2 actions, you had 4 actions, this sum will represent a sum of 4 terms. So the outer expression here will be 4 terms, and inside you will need to consider how many states you have. If you had, for example, 5 states, then this will contain, this number will multiply at a sum of 5 terms, each of these here. Okay, and this is simply given the s prime that you will consider at each time of writing these terms. You need to access the value function table to check what is the current value of that state s prime that you are considering. So this rule is very straightforward. Of course, if the set of actions and states is large, this is a large expression. And of course, if you are solving this with large state and action spaces, of course you don't have to write the expression explicitly. What you would do is just implement a for loop for this sum for every possible action, and inside that for you will implement another for loop for each of the possible next states s prime. Okay, so consider this example, this small grid world. In this world we have 4 possible actions to go up, down, left or right. We have only 14 states, and these gray squares are considered the terminal states or the goal states. The reward function is going to give a -1 reward after every transition. Okay, every time you move around you will receive a -1. So in this example, we're going to see how this algorithm, this iterative policy iteration algorithm, can be applied, and how the values for each 14 states are computed. For this experiment, we are going to use undiscounted development equation with undiscounted factor. So undiscounted means that the discount factor gamma is going to be 1. So the non-terminal states are 1, 2, up to 14. The terminal states are the gray squares, and this is considered to be, in this example, is considered to be only one state, one terminal state, but it is like in 2 positions. So the point is that once you have reached the terminal state, you finished your episode. Actions that would take the agent off the grid leave the state unchanged. So if you are, for example, in state 13 and you apply go down, the agent remains in state 13. The same for left and right and up action. So if you are in 8, you apply left, you stay in 8. Or if you are in 1 and applies up, you remain in state 1. And as I said before, the reward is going to be -1 all the time, every time you move, every time you apply an action, actually, and until the terminal state is reached. Okay, so even when you apply, for example, here in 14, you apply go right, you will get again -1. If you are in 14 and you apply go down, you get -1, even though you remain in state 14. So if you implement the algorithm and run the experiments, this is the value function in the first iteration, v0. Initially, all of the values are initialized as 0. And if you derive the policy from this, you will get these movements. So one important point, this greedy policy is saying, okay, given the current value, if I am in some state, what is the best movement I can make to get the largest value, to move into the state with the largest value. Okay, so this is telling you, if you are here, for example, is the same if you go left or you go down or you apply go right or go up, you will remain in a state, or you will move into a state with value 0. So it's the same, and that's because we don't have information yet. But after applying our algorithm one time for one sweep, now we have this value function, which is -1 everywhere except the state terminal states, this one here and this one here, because we are not updating the values for those states, so they will remain with 0. We will update only the values for the states 1, 2, up to 14, which is this one here. So at this moment, the policy starts to change, because now if you are here, the best movement is to go left, because it's the largest value. So if you go right, you will get a -1. If you go down, you will get a -1. If you go up, you will get again a -1. But if you go left, you will get a 0, which is larger than -1. So it is better to go to -1, to 0. The same happens if you are here. The best movement is to go up. And something similar happens with these neighboring states, neighbors of this terminal state. So if you are here, the best movement is to go down. If you are here, the best movement is to go right. Then if we perform another sweep, in iteration 2, the values change again, and if we compute the greedy policy from this value, you will have this one here. If you apply it one more time in iteration 3, you will get actually what is an optimal policy. So with 3 iterations, you can already generate the optimal solution for this MDP. And what we're seeing here is that if you keep updating the value function, like for example, this is in iteration 10, the numbers will keep changing, but the policy is not going to change because you have already found the optimal policy. Okay. So you can keep updating this and the policy is not going to change. So what we need to identify is that we have already found the optimal policy, and you can do that by comparing from one iteration to the next one the policy function. Okay, so that's another way to know if you have found the optimal policy once the optimal policy is not changing anymore. Now this MDP is a small MDP, so you can perform sweeps very fast. You have only 14 states and you have only 4 actions. But when you have a large set of states, like let's say you have a problem with 1,000 states or 10,000 states or maybe millions of states, then running sweeps, so updating completely for each of the states, it's time consuming. You will see you can apply this rule in an asynchronous way, which that means don't apply a complete sweep, just apply the updating rule, the value updating rule to only a subset of states in each iteration. So if you do that, then it is difficult to see or to determine if the policies are not changing or not, because maybe the change from one iteration to the other depends on the selection of states that you updated. So that's why this criteria to stop the algorithm could work if you apply complete sweeps, but it does not work if you apply asynchronous sweeps or asynchronous updatings of the value function. So now let's talk about policy improvement. Suppose we have computed some value for a deterministic policy pi. For a given state S, would it be better to do an action that is different to the action suggested by the policy in that state S? So it says, okay, so you have some value function like in the previous example, and you take an action that is not the one suggested by your policy. Would that be is that okay? Is that good to perform an action that is not the one suggested by the policy? So the answer is, it is better to switch to that action if and only if the Q value for that pair of state and action is larger than the value estimated by your current value function. Okay, and this Q value is simply the expected return that you will get if you follow the policy pi and you have this current value function. And this expectation can be calculated with this sum, in which you will have a term for each of the possible states. And this is the transition function, this is the reward function, and this is the value function. This P and this R are the same that we saw previously. The only difference in this expression is that we don't have here the policy function, because we have already selected an action here, so we don't have to calculate the possibilities of selecting an action in that state. We have already selected an action A, and this is the one that we are going to use here. So that's why we don't have the sum here on the left. So if this value is larger than the current value that you have estimated for state S, then you should switch to the action A, because that means that that action is better. Okay. Do this for all states to get a new policy pi prime that is greedy with respect to the value function v pi. So this pi prime of S will be the argument, so the action that maximizes the Q function for SA. And as we saw previously, this Q is computed with this expression. So if you perform that for every possible state, then you will get a value function that will be larger or equal to the previous value function, because we have changed our policy. And this is what we call the policy improvement. What if once you have applied policy improvement, the new policy is the same as the previous value function for all the states in your state set? Okay, if you do that, that means that the value that you have found with your policy pi is the value function which is optimal, is the v star, the optimal value function. And both policies, policy pi and policy pi prime, are optimal policies. Okay. So you can perform, which is the second algorithm, in one iteration you can perform policy evaluation and policy improvement. Once you have done that, you have the next version of your policy and the next version of your value function based on that policy. And you keep doing these two steps, policy evaluation and policy improvement.